introduce Alejandro Lopez Rincon. I hope I pronounced that more or less good. Yeah, you will talk today about the use of artificial intelligence in COVID-19 research. So please go ahead.
So, hello everyone, thank you very much for the space. If at any moment you want to ask questions, please go ahead, because it's easier. Also, I do know that it's the first time I'm here presenting in the complex system, so probably the math people and computer people, you know more than me. So please be kind. I'm Alejandro Lopez. I'm an assistant professor in pharmacology, so it's more towards the applications in pharmacology, okay? So, okay, I'm gonna start with this. Convolutional neural network. So convolutional neural networks, they are a computer vision algorithm. Basically, it works like the human eye, and they are overlapping windows. So many windows to be able to detect something. When the COVID-19 pandemic started, there was a big problem because it was very difficult to distinguish between the different coronaviruses. There are 7 coronaviruses, which 2 of them are the common cold. So people will go to the hospital and they will show symptoms, but how do you differentiate from common cold from COVID-19? So that was one of the problems. So an idea was, this is the sequencing of someone from the virus. This is the virus, basically. This is the sequencing using next generation sequencing. And the way that we distinguish is to finding small sequences that are only appear in the SARS-CoV-2. The intention was to finding this sequence of 21 letters, for example, in 30,000. So SARS-CoV-2 in itself has 30,000 bases. So the intention was to find this, and the first idea we had was to use computer vision, a convolutional neural network. So we input the text and we find it. So convolutional neural networks, the original algorithm was made by Rincon, and basically this is the basic one, which is used with the NIST database to be able to detect characters. So, well, technically numbers, this one. So we will have the original image. From the original image, we're gonna take apart, then we're gonna do a convolution operation. I'm gonna explain a little more what a convolution operation. Then we're gonna have subsampling, so that subsampling can be something like max pooling. Then we have the full connected layer, and then we have the output that we classify. Like, for example, if we are trying to distinguish numbers, it's gonna give a probability of which number it is seeing in the image. Now, if I wanted to go back to the example of trying to find a sequence in the SARS-CoV-2, we will have to code it in order for the convolutional neural network to understand it. But basically, here, so we need to code if we're trying to detect characters, for example, we're gonna have only for each pixel 0 and 1. In this case that we have bases, we give these values between 0 and 1 for each of the possible bases. So for example, we're gonna have 4 bases, C, T, A, G. We give these values, and in the case of a missing value, we give a 0. Okay? So this is how we code the genetics into something that can be used by the convolutional neural network. And this was, when the pandemic started, we only had 66 sequences of the SARS-CoV-2, and this is what we use to try to separate SARS-CoV-2 from the rest of coronaviruses. Okay? So we have the genetic material, we have the database, we code it like this, and we try to separate it from the rest of coronaviruses. This is what we want to do. So we use a very big model with convolution, max pool. It worked, but was this useful? That was like the question. Computationally, it was working because we were able to separate with a very big model. We were able to detect SARS-CoV-2. But the question was, is this useful? Because that would mean that we have to take a sample from a patient, separate the virus, sequence it, and then compare it. And, well, these are the metrics. So basically, we have an AUC of mean AUC of 98%, which is a diagnostic measure. So 98 means that it's very high, that we were really able to separate. Then if we were able to separate the classes, if you remember, we had 66 from SARS-CoV-2, so we were able to detect 63 out of the 66. So computationally it was working.
Sorry, can you explain one more time how big is the sequence you are using to detect whether it's SARS-CoV-2 or not?
21 bases.
Oh.
And SARS-CoV-2 in general is the biggest. Well, I don't know if they're bigger, but but in that moment, the literature said that it was around 30,000 bases, making it the biggest virus. So we needed to find 21 bases.
The coronavirus
Yes.
is the biggest one, indeed. Yes.
So
It's only 21 base pairs, so.
Mhm.
Okay.
So we needed to find 21 base pairs out of the 30,000 that were specific to SARS-CoV-2. That was like the problem. So first we used a very big model that had several layers, but then we reduced it to the minimum,
Mhm.
which was convolution, then a max pool, and then a fully connected and softmax. So this part fully connected, that means that the output of the max pooling, I'm going to explain the max pooling. The output of the max pooling, all of them are interconnected, and then when we do the training of the convolutional neural network, it's going to be connected to all of the outputs from the max pooling, and with the training, some of them are going to drop out. That's a dropout. Also, dropout is a type of regularization, and a softmax is just to transform the probability of which of the coronaviruses it is. So that's a softmax layer at the end. So these two, let's say, are the standard in any neural network for the people that are more used to neural networks and more in the AI part. But here the interesting operations are the convolution and the max pooling. Again, our detection was very good. We had 64 out of 66 using this model that it was only convolution, max pooling, fully connected, and softmax. Okay. However, again,
Can I ask, so how does this compare to other methods? If I would do random forest, for example, would it be like, I don't know, 0.5 the AUC, or do you have any idea?
the classification. Actually, I'm gonna move into that because the point is to show that this was not necessary.
Oh, okay.
So again, this computationally, we have very good results, but how do we translate these results in the computer to something that is actually useful during the pandemic, right? So again, the metrics are really good. We are able to detect 64 out of 66. Our AUC is 98. The model is simple. But what does this mean? So if we make a graph of the 4 bases, and these are the sequences all arranged, each row is a sample, okay? And we put these colors. We only have technically 4 colors, but the combination, because of the pixels, because they are next to each other, is gonna compress it. And these are only the sequences from 0 to 1,250 base pairs, and this is from 1,250 base pair to 2,500. It's less than 10%. 10% of the genetic material of the SARS-CoV-2. This is how it looks. You understand? So basically what we're doing here is I take this and I put it as a single line, and I do this for each sample I have. And these images that I'm showing are just the first 2,500. Just, let's say, graph. We put a color for each base. Yes.
Shouldn't you align them first to get a better pattern? Because maybe there are insertions and deletions, and that's why I see some of the shifts, maybe.
Ah, we're gonna get to that too.
Okay, oh, okay. Okay, I was.
Perfect. That shows that someone is paying attention.
I'm paying a lot of attention.
So the missing are black, but we're not doing any alignment. So we're just we just want to show the information how it is. This is how it looks, the virus. And here we have 6 groups. Okay? To be clear, these are the groups. So SARS-CoV-2 is group 0, MERS is 1. These are the number of samples. all of these that are not so common are 2. Then SARS-CoV-1 or SARS-CoV alone, that's the last group. Sorry, we have 5 groups. Okay? So we are here. And here I would like to, for the people that are in pharmacology, to explain what a convolution is. At least this is how it is encoded in TensorFlow for the people that are into this. Basically, you have your window, and you have a smaller window that is going to move in your image. Okay? Which is your original image will be the blue part, and the smaller window that is going to move is the green part, that green square. So this, it doesn't get to show, but there's a pink square over there. That pink square and that green image, they roll out, and they are multiplied, dot product, and whatever it comes is what you put in that part in the center. If you move this green square to the right 1 pace, just move it 1, then what is going to change is that green part. Now it's going to be those values you multiply, and it's going to be, instead of here, 1 to the right. That is a convolution. That is very basic convolution. There are many ways to do it. Well, depends on the complexity, but this is convolution. And max pooling, which is the reduction, it means these are the values that I have. And if I apply a max pooling to this square, they will mean from this section, I take the maximum value, 20. From this section, I take the maximum value, 30. And this is the max pooling operation. So what does this one do? Reduces the image. Okay. This is the initial 1,250 base pairs. This is divided into 5 groups. No alignment, no nothing, just how it enters. If we go to the model, we have 12 convolution weights. These 12 convolution weights, when we apply them, actually I'm gonna show for the first 2. This is the output. Consider a convolution size 1 to 1. This is weight 0 and weight 1 from the convolution. Here, well, maybe it doesn't notice as much from your angle, but we have some edges. We have some lines. Those edges. This is after multiplying by convolution. So let's focus only in weight 1 or weight 0, as we prefer in computer science. So these are the edges. When I do the max pooling, when I do the reduction, it's going to look like this. And you can see that here, talking about the alignment, visually, we can already separate it. You see? These patterns, just by looking at this pattern of the first 2,500, we can see in which group they are visually, us. So, after the max pooling, we are able to classify. And if we put only the edges in the original base pair coding, remember that we put a color, looks like this. A line. So,
Is it? I don't know.
well, like for example, you can see this orange, you can see this yellow here. This yellow here is different from this, you see? You can see here the groups. It's easier if we separate it.
So, and then each group is a different coronavirus?
Each group is a different coronavirus. Okay, so why this matters? These edges that help us do this pattern, maybe if you compare this pattern to the original patterns, like for example, you can see that all of this, how it's the orange followed by the red followed by a yellow. And if I compare it to the one below, it's yellow, green, brown, brownish. So just like this is very different, this and two. You see? It's something that we can see. This is going a little into trying to explain what the algorithm is doing. If we take both, if we take this edge and we go, this is if we take only the edge and we get the exact base pair that was detected at the edge. But if we go to the original file, to the original sequencing, and we take 10 letters before and 10 letters after, 10 letters before and 10 letters after, we get 21 base pairs that we can use as pseudogenes. Okay? And these pseudogenes of 21 base pairs is going to help us change from using a convolutional neural network to now doing feature selection. So we're going to translate these 30,000 bases into 3,827 pseudogenes. Okay? So now we're going to move into that. So why 21? In PCR, I think many of us know at this point what a PCR test kit is after the pandemic. Normally they are between 18 to 23 base pairs. They are some cases which they are smaller. There are some cases which, well, normally smaller is not as common, but bigger, yes, to be able to detect. So how do they detect? They attach a forward sequence and a reverse sequence. Basically, they attach and they say, okay, if these two sequences of 21 attach, then I'm detecting, for example, SARS-CoV-2. So the intention is we need to find a specific 21 sequences that only exist in SARS-CoV-2, which is the next step. So again, if we go from the edge, we create pseudogenes, and then we transform the problem into feature selection. Now, one of the things that we do a lot, my group, is recursive ensemble feature selection, and we have compared it to other methods, but I find it very interesting that it comes from the Condorcet-Urey theorem, which is a larger group is more likely to make the correct decision when individual voters are competent. This means when they do not have a bias. How does this work? Basically, if you want to get closer to the truth and you have a lot of people, but they do not have a bias coming in, and you make your arguments, they're going to make the best decision. At least this is what they thought in the 1800s and not now with how we vote in general elections in most of the countries. But this is the idea. Using this political science theory, we apply it to artificial intelligence, and then we say, okay, what happened if I want to find features? I'm going to do a ranking of the features using several algorithms of machine learning instead of one. So we use 8 classifiers, and then we divide them into 2 types, the ones that have coefficients inside of them, the ones like they make decision tree, although bagging in something is an ensemble. And then we rank the features. So how do we rank the features? So how does this look? Well, this is from the Cancer Genome Atlas. This is just a comparison of how the classifier ranks the features. It has 1,000 features, and we were trying to detect 20 types of cancer. So this is the top 100 features. But we can see that there are some features that all of the classifiers agree. These are 8 classifiers. The darker, the most important for the classifier. The whiter, the less important. So you can see these features are very important. Whereas these features, as we move into the axis, they are less important. And these are the top 100. So these features where all of the classifiers agree, those features are what we're going to use, for example, to classify between different types of cancer. This is an ensemble. This is how we do the ranking. And then we run the algorithm 10 times. And we select the best set of features either by accuracy, matrix correlation coefficient, which are metrics. Like accuracy, I think everyone can understand. Matrix correlation coefficient gives an idea of how well it separates the classes even with class imbalance. So it's gonna say, okay, depending on the matrix correlation coefficient, we can make a decision. Actually, yes, I have here a comparison. So this is using accuracy, matrix correlation coefficient. And again, this is how the features are ranked. Okay, this is the only part that matters. It's not to go in the details. So we apply that to our original 3,827 SARS-CoV-2 pseudogenes. So we're here, and we want first to separate between all of the types of coronaviruses. So we find that from these pseudogenes, we only need 53. I'm sorry, this curve is because I haven't updated. It's not as pretty, but what it says, the accuracy, it's the maximum accuracy, that a smaller set of features is 53. Okay? And with those, we can separate. However, we were interested not in separating all coronaviruses, but SARS-CoV-2. That's it.
So why do you take 53? Because I see that it becomes 1 earlier, or not?
No, it's because, well, that's why I said the graph is not such as we call it,
okay.
but because it's only X.
Okay.
There's still some variance. That's the point where
Okay, and then the different lines in the graph is for different
runs
different rounds. Okay.
runs of the algorithm. So we take the best set of features with the best accuracy. Okay? And these, yes, please.
The features here are 20 base pairs. Or
21 base pairs, our pseudogenes.
so these 53 are different 20s of pairs.
Yes.
That's all. Okay. Yeah, thanks.
But instead of coding it, we only code how many times it appeared the pseudogene. You see?
Yeah.
We have a dictionary of 3,827, and we only say, okay, this one appeared 3 times in this 30,000 letters. This sequence of 21 only appears 2 times or 5 times. So it transforms it into a dictionary. Actually, next generation sequencing overall works like that. We have our genes, and we match how many times the genes appear. Okay, so, but coming back, here we try to separate between the 5 groups. But what we were interested is to find only SARS-CoV-2. When we do that, and we compare it to many of the sequences we find in NCBI for other viruses. So for the people in pharmacology, every virus that has ORF1ab and host Homo sapiens and complete genome, we compare it to everything in NCBI, and actually we got, for each run, a different sequence. What does this mean? That any of these sequences can help us separate SARS-CoV-2 from any other virus that has gene ORF1ab and host Homo sapiens. So in this case, it was 339 comparisons. We went further and we compare it against all viruses available in NCBI, which is 20,571, and we find these 2 sequences. So these 2 sequences are unique to SARS-CoV-2. They only exist in SARS-CoV-2. We compare it, so these are our 12 sequences, the 10 from the first, then the other 2. We compare it to 1,256 SARS-CoV-2 sequences per GSI. And they, well, some errors there, but these errors are like missing values, stuff like that, but most of them are above 99% unique to SARS-CoV-2. Please.
So what part of the genome are these sequences actually found in? Like, is it a very conserved region or?
It's in the, I'm gonna get to it. So first you're talking about finding sequences that only exist in SARS-CoV-2, right? So, yes.
Yeah, and why do you need machine learning or feature selection to do that? Like, just look at the sequences once you do the alignment and check the ones that are unique to SARS-CoV-2.
I'm gonna touch that too. Okay, so that's the first point. So right now, machine learning, I'm gonna put it aside, but the deep learning was not necessary. We could just start like from the set of genes, and actually afterwards it gets simpler and simpler, but I'm explaining the whole thought process of how we get there. So these sequences, we can use them. And then having these sequences, we can simulate it in primer 3+ and generate already a PCR test kit, which is what we did. We generated a PCR test kit that could be used. Now, for the question you were saying, it was following studies, we use the ORF3A gene, which is a conserved region and is not in the outer part of the virus. So it was resistant to mutations. And I'm gonna touch on that. And I'm gonna talk the alignment, for example, when you have the SARS-CoV-2, the original primers, they didn't work. They stopped working very fast. And that was one of the problems. Because if you only do alignment, maybe it favors the part that mutates a lot. We're gonna get to that. Just a second. Let's continue here. So we actually generated a primer set and we tested in a lab. We tested with patients. We compared that. In summary, this image just shows that we were able to detect SARS-CoV-2 and only SARS-CoV-2, not other coronaviruses. Okay? This is what it means, but we are already using samples in a lab and just a PCR primer test kit, so we do not need a computer. So the whole process was from the sequencing to the deep learning, from the deep learning to feature detection, to here finding specific sequences, to the primary design, and the laboratory testing. Okay? So now we started testing the primers in different places. So we tested Mexico. Well, I'm Mexican. So the people in Mexico were willing to test it. And we compare it to commercial primers. So I'm gonna go a little fast on this. We have 15 examples that we knew it was SARS-CoV-2, 5 that we knew they were not. We compare these commercial brands that target these genes. Us, we target of, yes?
Did you use those two final primers that you found had no overlap with the other viruses, or did you modify them? Because I know from experience that there are quite some other restrictions on a good primer in terms of melting temperature and other chemical properties. Did you modify them?
So we have 12 sequences in the end that were working. We just simulate them using primer 3+, and primer 3+ controls for the temperature, controls for GC content. Sorry, it's because to remember all that.
But so primer 3+ is a program that changes.
It's a primer. It's a program that tells you, hey, this primer is gonna work, yes or no, and helps you create the reverse sequence too. So we use the sequences we found, the 12 original sequence we found, like, okay, these are unique to SARS-CoV-2. We use them to generate the primer, the reverse sequence too, and they generate the primers. But we simulate all of them. And with primer 3+, this was the best bet because of the position in the ORF3A gene. In comparison, I forgot the name of the gene that is on the outer part of the SARS-CoV-2, because that one mutates a lot.
Spike.
Yes, that's gene.
Thanks.
So these are the numbers, which is not my expertise, but the people in the lab said it worked. But let's go a little more into frequency of appearance. So as we move forward, GSI, which was an international repository, at this point, for example, had 17 million sequences, I think. But in the beginning, every week they added a couple, and the beginning was restricted, so we had to hack it. Anyways, we got all of the sequence, I don't remember at which point in time, and these are all of the different variants. Okay? The original primers, which are this one from the CDC China, you can see that by alpha, B117, they stop working. So they need to work, the forward and the reverse, they need to work in order to detect. So this one, the forward from China, you can see in which variant it stops working. These ones are ours. This was a variant that didn't spread a lot, thankfully. Actually, it was very few sequences, and it was basically contained to one country. But afterwards, moving forward, like until now, the ones that we designed, they continue working. So what does this mean? We have all of these are the forward and reverse sequences for different primers, different brands, including the ones that we designed. These ones are the ones that we designed. So depending on the brand, if the value is 0, that means that they do not detect. So both forward and reverse need to be detecting in order for it to work, in order for someone say, has COVID, yes or no. Do you understand this? So both sequences of forward and the reverse need to detect, need to have a match, or it will simply say, no, you don't have SARS-CoV-2. This is how it works. So both forward and reverse. So this one stopped working really fast. The other ones work quite well. Variants. So let's go a little more into variants. And let's go a little, why do we need machine learning? Well, still we use genetic algorithms that just find the statistics. So after this experience, we started to try to catch and generate primers for each of the different variants of SARS-CoV-2 because it was mutating a lot. So we came to, okay, we need from 8 to 12 sequences, and with that we can generate primers specific to a variant. Any of the variants like alpha, beta, or omicron, whatever. How did we do this? So using genetic algorithms that right now I'm not gonna explain. We find a position in a sample, and we check it was unique to the variant we're targeting and not to the rest. It can be done brute force, basically, yes, but takes more time. This one, so we were able to design primers in around 4 hours for any of the variants. And for example, for B117, we generate one that was specific for B117. And these are more examples. And all of them we tested in the lab. And yeah, they were working. They were specific for the target variant, which is it's important in the sense for future pandemics, this can be used. Like very fast, we can detect primers. Actually, for monkeypox, we detected and we put, hey, with these primers, you can measure in case you want it. The information is there. So, this part, okay. Yes.
So in your big matrix of performance, you tell what at the bottom, the Chinese ones had problems. There was a lot of commercial ones that were working perfectly. Do you know what are the primers they are using, or is this trade secrets?
It's the law says that they do not have to say which sequence they are using, but if you discover it, you can use it.
Okay, yeah.
That's the law. It's like the actual sequence, they will not give it to you, but if you find it, they cannot do anything. One of the things is the commercial ones, they work to detect SARS-CoV-2, but in the case that detecting Omicron, you need like very specific, and they were using these ones that detect several mutations at the same time, but they are more expensive and all this. And also some mutations, because this was done in the beginning, and not like, for example, now, this has a couple, years at this point. If we update it, ours continue working because they stay in ORF38 gene, and some of the commercial primers do not. Actually, the first primer, one of the first primers that was used here in Europe, it was by Molenkamp in Erasmus, which was, they took the SARS-CoV-1 primer and they modified it for SARS-CoV-2. So this is an example, and also I wanted to show that train of thought of how we got there. So we didn't know how to tackle the problem. So first we tried computer vision. Then we try, okay, we cannot be running a convolutional neural network every time that we have a new sample. So how do we actually change that into making a test, a physical test that doesn't require a computer and you can run it in the lab? That's the interesting part, at least for me. Now I'm going to talk a little more about feature selection. So this is the current thing we're doing, long COVID. Many people debate, long COVID was real, yes or no? Well, now we know it's real. In the beginning, people would say, you're just exaggerating. Yeah, you feel tired. Yeah, I feel tired too. The classic, right? And then we already have this disease that is called chronic fatigue syndrome. That actually, if you go and you read, chronic fatigue syndrome appears in a percentage in people that have suffered a cold, mostly with a coronavirus. And after they get healthy, they have symptoms of being tired and it feels like their body is still fighting the disease, but the disease is no longer there. But the interesting part there is a coronavirus. So SARS-CoV-2 being a coronavirus, this is the connection long COVID and ECFS. So now the studies are towards, okay, chronic fatigue syndrome is the same long COVID. Some authors say yes, some authors say no. The last, they said no, there are different things. There are some genetic studies, like from this year. And using one of those genetic studies, we try to separate regular people that had COVID but get healthy to people that got COVID and got long COVID. Okay? And the intention is, what can we do, because we're pharmacology, what can we do to mitigate long COVID? This is a research question. So we take people that got COVID against people that didn't, and we check the genes. We do feature selection again. The database is data ascension number. You can go check it if you want. It's on the internet. It has 785 genes, right? That I measure in immune exhaustion panel. 15 have long COVID, 18 do not have long COVID. We do feature selection, all of that part that we find the most important features. In this case, the features will be genes, which is okay, we find the most important genes. And then in the end, we use a classifier that was not part of the ensemble of what we used to select the features to check how good it was in diagnostic part. And we get a very nice mean AUC. However, we used two other databases with those 7 genes to see if we could separate long COVID from, well, people that had COVID but got better. Here we call it controls. Controls against long COVID patients. And it continues working these 7 genes. But in 2 databases that are not the same, not the same lab, not even the same city, which is very good because many of these studies is like non-reproducible. But in this case, our technique, one of the things that we try to make an emphasis is that we can do this. Like we take these 7 genes, we apply it in other 2 databases, it works. So, the pharmacology part. These are the 7 genes. And I do not know what genes are gonna come out, and I do not know anything. Just, I get the 7 genes and I check, okay, are these genes connected to COVID-19? Yes. These 5 genes are connected to COVID-19 already. And there are studies that paint these 7 genes. And actually, we take one, this one. And I go to a repository, and in the repository it says, okay, you can target this gene with these 2 drugs, sarilumab and that. So we target that gene with these drugs. And actually right now, this is on research trial in the UK and the United States. And this one, there's already literature that defends that it can be used for the treatment. So again, how do we go from a database to something practical? At least we know. Afterwards.
So for some of the genes, they are higher in long COVID individuals, and then the others are actually lower in long COVID individuals, right? Or
Mhm.
okay. And then does it kind of make sense? Like IL-6 receptor is lower in long COVID individuals.
Following this database, yes. However, in another database, it was, I think, the opposite, but had to do with the batch error.
Yeah.
However,
But,
later,
so I just don't understand. You say sarilumab,
Mhm.
that's a high affinity anti-IL-6 receptor antibody. So
Mhm.
that indeed blocks IL-6 receptor.
Mhm.
But if I look at your graph, for example, it looks like people that do not have long COVID high expression, and the ones that have long COVID already lower expression of IL-6 receptor, and then just blocking it even more, that just doesn't sound intuitive to me that it will help the disease, but I don't know. Am I the only one that confuses or? Okay.
this is very pharmacology, and again, it's beyond my expertise. However,
I think
They are all-
this is more a little bit logic, I think, right? I mean, you have a receptor,
Mhm.
and the people who have the disease already has lower levels of this receptor than people who are healthy. So I would think if I want to cure these people, I need to increase the level of receptor because healthy people have more.
What you
But-
don't know here is
Yeah.
how the expression levels were calculated.
Yeah. What?
You don't know how the expression levels were calculated. It must have been normalized by the people who did not get COVID.
Yeah.
And,
I
you know,
get
is
that.
it in a denominator or numerator?
Yeah, but I'm just
But-
trying
but
to
your
get at
argument
least
makes sense.
the logic at
Yes.
least, trying to
No,
make sense of it.
Maybe it's a receptor internalization because of the exposure to IL-6. And if it's too overwhelming, the receptor can be internalized. So it
Yeah.
can be also be the relevance here. So
Yeah, I
it's
can
already
imagine
already-
that I mean, it might be relevant, it's just I don't understand if you have an antibody on top of it that blocks the receptor, how would that help the disease then?
So it is maybe already internalized.
Yeah.
So the expression is lower, but
Yeah.
still, when it's being activated, it keeps on going. So block the receptor that is left over. It will maybe help to.
Yeah, but healthy people have the normal receptor level,
No,
right?
that's what I mentioned that, and also has more connected to him. The other database, although it's I can use the same 7 genes to classify. It was the opposite. I'm not using my own data. I'm using data available in the internet, and I can say these genes are connected to long COVID, but it needs further research. However, the thing that I can say for sure is that this gene, for example, IL-6, actually those 5 are already used in trials as targets for long COVID. But this is more in the specialty of pharmacology. Yes, please.
So, I mean, now you have some of these genes that aren't connected to COVID in the literature. I mean, did you do any sort of like pathway analysis with these genes to try to see if maybe those other 2 targets somehow connect to the same pathways that the other genes are involved in? Or did you just sort of neglect them because they're not connected?
No, I do it separately from the pathway analysis. Because many of the studies of pathway analysis are non-reproducible. So I try to stay in the gene expression part.
I don't think I understand. Like, I mean, after you found those genes, do you then try to connect it back to the biology and say something about, well, you found some targets that have already been associated with COVID, and then you have some targets that aren't highlighted there that haven't been associated. And did you try to then figure out, can we figure out if they might be associated by linking them in the same pathways as genes that were already associated?
Yeah. Yes. Yes. However, it's, for example, yes, that you go and you look into the literature research and see, okay, this gene affects another one that is in the pathway that we already know. However, I treat these genes as a single signature that is separated from the pathway analysis. If you go and you do, for example, algorithm IWGCNA, which gives a weight to a pathway to select the genes. The part of the biology, yes, is very important, but that's the next step. So my step was to find the genes. Right now we are in that part, exactly what you're saying. Like, okay, I find the genes, I find that people have found them too. Why? But normally my expertise ends here. Then I ask people from pharmacology, molecular biology, hey, does this make sense? Because hey, I find these 7 genes that help me separate long COVID. Imagine separating 7 genes from 20,000 to 60,000 genes. Okay? Finding 7 genes that if you
But I mean, it wasn't
check,
20,000, right? Because it was already a selection of immune exhaustion genes.
yes, but for example, in the other databases, there were 20,000.
But did you do like feature selection again, or did you say, okay, well, let's use the 7 genes we are already identified against all 20,000? Because that's a very different question.
We use feature selection again. We use feature selection again, but the results of the feature selection again separately. For example, now I'm using this one as a base, because normally we use the smaller one, the one with a smaller gene or smaller features as a base for the other ones, but I did the studies of the other database independently. Not all of the 7 genes match, because it gives priority to some that were not part of immune exhaustion, but some of them did. You see? However, this one, we're very happy because it worked in 3. And the other one, I cannot validate it in the other one because they're not even measuring those genes. When we have the whole panel, which is something more like, well, my student over there does, he's able to compare the whole databases like that. But right now I'm working, again, not with my data, this is what we find.
Well, I'm totally confused. Can you go back one more slide? Because then I'm trying to really, okay. So the first one is your validation, what was it called? Discovery set, right? So
Yeah.
there you find the 7 genes.
Yeah.
And then in the second data set, you use 7 genes to get these AUCs. Okay.
In 2 different databases.
And then in the third one, you again use the same
7 genes.
So, but you said that you are doing again feature extraction. Where do you?
No. The feature extraction again, like he's saying, I did not include it because it will make it a little confusing because we have different combinations to explain. It's easier to say, okay, I use this one as discovery set and I validate it in data set A and B.
Okay, I also don't understand the second and the third graph because you just say, for example, rock fold 3, that's then AUC of 0.5, and the rock folds, I don't know.
Because we run tenfold cross validation. Because these are classifiers.
Why do you then I mean, if you are not training anything new, why do you need to make cross validation? Because you take the 7 genes from your discovery set and you test it on the full second data set, right?
Yes.
So why do you need to make cross validation? Use all of the data.
Wait. So one of the things, because we're working with databases from different groups and different machines, we have to compensate for the batch error. Yes?
Okay.
To compensate for the batch error, we use only the solution, like these are the genes that I'm using.
Yeah.
And we apply a classifier. Okay, with these genes, in a tenfold cross validation, tell me, are you able to separate? So we have to train again. We train again to compensate for batch error. This is one of the ways to compensate for batch error. If we take the genes directly, like training and test set, we do not have the proper normalization because we do not have the raw files. You see?
Yeah, well, I guess I see. But I mean, so how do you imagine that you can then use it, use this as a diagnostic tool or so?
To make it a diagnostic tool, you have to say, is this machine? And you have to have samples from this machine in order to know the levels on that machine, a specific machine.
Okay.
And genes also beyond the machine have to do with the population. So it has to have the proper levels that you expect from the population over there and the machine that you have over there.
Okay. And maybe we should move on.
No, here I finished because.
Okay. Okay.
I guess, to come back to your comment with biology, you are detecting markers, basically. It doesn't mean there is a causality or whatever. That's like correlation doesn't mean causality.
It's detecting markers. That's where I stop.
Yeah.
But then,
And
that's why, for example, SALA is going to help us. But yeah, so this is the type of things. It's very, well, coming more from an AI background, I really like this part, like, okay, we find some genes, 7 genes. And this time, okay, we started from 700, we find 7 genes. But sometimes we have 60,000 and we find 1. And then when we look and we check that 1 gene, it's like, we can see like, oh, it's in clinical trials. So you have this validation like, some people find the same, but in a completely different way than mine. So more or less, this is what I wanted to focus in this talk. So it's not just the numerics, but try to show how it's actually used. That's why in the other one, we went, okay, these are the sequences of SARS-CoV-2. How do we do an actual primer test that we can use in the, and as you said, is how do we actually use it as markers? Well, you will have to say, okay, we're using this machine under these conditions. But let's start by targeting these 7 genes. Okay, thank you very much. I hope you like it.
Let's stay around a bit longer for questions, but we want to thank you for the call. And if anyone of you would like to present during one of the science camps, you can also contact us at CPS.
And please, more specific questions, send me an email.
So, if it was not correct, you have found something. If you have a non-COVID patient, then he has these genes in his virus. Is it also the other way around? If you find these genes in the virus, it's a non-COVID patient?
Oh no, it's different. It's different set of genes. In the first example was SARS-CoV-2. How to find SARS-CoV-2 with a primer test? How to design the primer test?
Yeah.
In general.
Yeah, that was.
So the genes in viruses are different from the genes in humans. In the other one is more like using a next generation. Because
No, I mean, the last thing we discussed.
So
that was, I thought that was genes that were present in the long COVID virus.
yes.
So what were present in the COVID virus, and if it was present there, that was found for people that had long COVID. Is it the other way around also? If you find it in the coronavirus, then the person that had that virus will develop long COVID.
One of the manuscripts I'm working in is, it makes no, I'm gonna say, it makes no sense biologically because it's a missense mutation. So a missense mutation technically doesn't affect the workings of the virus itself. However, this missense mutation in combination with another mutation, maybe I said it wrong, but this is how I understand. So a missense mutation, but are actually changing mutation, I do not know the proper term. Those 2 patients that have long COVID, also the virus, when sequenced, have these 2 mutations. So it's the virus has something that produces at least very serious long COVID. The virus has something. So there are people that have studied this. In my case, I found a missense mutation. What is the definition of missense mutation? You know it better. So missense mutation, if I understood correctly, missense mutation doesn't make a functional change. It's something different in the virus, but doesn't make a functional change. This is how I understand. But the people that have been in, at least reported in GSide, that have been in ICU, have this missense mutation, the virus, when they sequence it. Because they have at least attached, like, has this person been hospitalized? Yes or no from COVID? So this is something that I'm studying.
Is something?
I'm studying right now. So I have the part of long COVID, like, okay, this 7 gene can be targets, and I end up here. And on the other part is like, okay, the SARS-CoV-2 as a virus has these mutations that altogether people, at least with a probability, end up in the ICU.
So is it like the combination of the genetical susceptibility of the patient together with the mutations in the virus that combine?
Sadly, I wish I had the databases to match, but I only have, for example, for one part of the virus, I only have the sequence of the virus, the 30,000 base pairs, connected to if they finish in ICU, yes or no. That's the only thing I have. And in the other sense, I have this part, but it has nothing from the virus. I have the genetic material of the patient, they finish in the ICU, or let's say long COVID, but I do not have the genetic of the virus too. Because it would be amazing to be able to connect, okay, this virus, this person, this virus, this person. Yes, but
Yeah, so I have the same question as to like why use machine learning and not just deep learning, as opposed to like I'm trying to understand if there's something more to the problem aside from sequence matching, essentially, because there's oh, and also how did you get the 21 number? Can you remind me?
the 21 number is something from biology. When you do PCR test kits, it has to be between 17 and 23.
Right.
That's the sequence that has to match for it to attach.
And so the total sequence length is 30-something thousand, you said?
The original sequence of the virus is 30,000.
And so you just, if you just slide the window of 17 to 21. Roughly.
This is how we do it, like at least now that I said, I'm not gonna explain it. This is how we do it. You can do it technically with brute force, which is run all of the possible combinations.
Yeah, like how computationally
Intensive?
more intensive would that really be? I can't really.
We discovered a midpoint to finding these sequences was using genetic algorithms instead of brute force.
Right.
With genetic algorithms, the parameters are which sample and in which position.
Okay. But still, like brute force wise, would it be like? Do you have? Is there like a baseline of how how many operations this requires? Because there's 30,000, so you have like you have how many, like 17, 18, 19, 20, 20, so like
I know, but
right? So you have like 5 times 30.
But you have to compare it. You have to compare it. It gets bigger and bigger because of the variance.
Yeah, and how many variants do you have?
Well, the last time I did this, I was still working. I think I was working 100,000.
Okay.
I see. With genetic algorithms was a midpoint because my colleague that actually is in in France, he did the brute force just to compare, and the brute force was better because it's brute force, because it can add certain specific things. Like in the beginning, we were not thinking that was connected with the temperature, GC content, because if you add the rules of GC content and temperature, from the beginning, you can kill like half of the possible solutions. Okay? Adding rules of primary design since the beginning and then doing brute force. However, we compare times, but this was done like, because research is like, I do not know how I'm gonna need this again. And we got to the conclusion evolutionary algorithms is better. And for this, we actually won an award in artificial intelligence internationally for using evolutionary algorithms for this. And because they were used, and well, we were really happy because at one moment we appeared in the news and everything, specifically for this part. So the deep learning is to explain more or less the train of thought I followed to get to there. So in the beginning, it's like, I do not understand this problem because it was not my problem how to design PCR test kits. I had no idea. So I thought, computer vision, I can find this. But then after I did a computer vision, I said like, yeah, this is amazing, but it's not useful in a lab. No.
Thank you.